This is a short video about the first derivative test and how we'll use the mean value theorem to establish it. So speaking of that mean value theorem, so that was the previous video. If you haven't watched that yet, you should check it out. But we should recall it here. So the mean value theorem, what's it say? Suppose f is a continuous function on some closed interval from a to b, and we also want f to have a derivative on the open interval from a to b. Remember, that just means that f prime of x makes sense as long as x is between a and b. Then what's the mean value theorem tell me? If you've got a function like that, you can find a point c between a and b such that f of b minus f of a is equal to f prime of c times b minus a. And so remember, what this is trying to say is that you can find some point c between a and b where the slope of the tangent line at c is equal to the slope of the secant line through the points a, f of a, and b, comma, f of b. Anyway, so we're going to use that to prove a few more things here. So again, kind of more applications of the mean value theorem. If you remember from that video, I was trying to emphasize mean value theorem is pretty important. We're going to use it quite a bit. So the next thing I want to use it for is to show the following. So let's say I've got a differentiable function f on this interval I. So again, all that means is f prime of x makes sense as long as x is in this interval. Then there's a few things I could say. I could say that f's increasing on that interval if and only if the derivative is bigger than or equal to 0. And I could say that f is decreasing if and only if the derivative is less than or equal to 0. By the way, when I say increasing, I don't mean strictly increasing. That's different. So that's why it's okay if this derivative is actually equal to 0. Okay, so what we're going to do, we're going to prove just a, because the proof for b is pretty similar. So let's see, we've got an if and only if here, right? So we've got a biconditional, and what we're going to do is we're actually going to start with assuming this part and showing that f's increasing, just because that is the part where I really use the mean value theorem. So suppose that the derivative is non-negative for all x in your interval. So let's pick 2 points in my interval then, where say x1 is less than x2. Then what we'll do is we'll apply the mean value theorem to this interval from x1 to x2. So what's the mean value theorem tell me? There should exist some point c between x1 and x2 such that I plug it into that formula from the mean value theorem that you can still see up above in blue. So mine would say f of x2 minus f of x1 should be equal to f prime of c, remember the derivative at that point between x1 and x2, times x2 minus x1. And what are we going to do? Well, I know that f prime of c here, that's non-negative by hypothesis, and I also know that x1 is less than x2, therefore x2 minus x1 is also non-negative. In fact, I could say x2 minus x1 is positive, since it's a strict inequality up here that's highlighted. So therefore, what can we say? This stuff is a non-negative number times a positive number, therefore I can at least say it's non-negative. And why is that cool? Well, because I could rearrange that. If I add this to the other side, I get that f of x2 is bigger than or equal to f of x1. And the idea is that worked for any x1 and x2 in my interval, therefore my function is increasing on this interval I. So again, the mean value theorem was important to establish the only if part of this if and only if. Now let's do the if part. And so let's assume that f's increasing on I. So suppose f is increasing on I, and now the goal is to show that the derivative is non-negative for every point in I. So let's take 2 points x and c that are in my interval, and there's 2 things that could happen, and let's say that they're distinct as well, I guess. So what if x is less than c? Well, in that case, remember I assume that f is increasing, so that f of x should be at least, or I'm sorry, at most f of c. And so what does that tell me then? If I do f of x minus f of c, in that case, I mean, that would be a negative number here, but then notice also x minus c is a negative number since x is less than c. Therefore, you've got a negative over a negative, so you could say that this is non-negative. So that's pretty cool. And what am I going to do? So that's what happens if x is to the left of c. What if x is to the right of c? Well, again, because my function is, I've supposed that my function is increasing, therefore f of x should be bigger than or equal to f of c. And again, what do I get? Well, when I take the difference then, right, f of x is bigger, so now this is positive, and remember now x is to the right of c, therefore x minus c is positive. So therefore I can at least say that this is non-negative. I probably should have been a little bit careful. I can say that this is non-negative because f of x is at least f of c. So again, the point though, something that's non-negative over something that's positive, since x is bigger than c, therefore this fraction should be non-negative. So what am I trying to say? I'm trying to say that no matter what, whatever side of C that you're on, f of x minus f of c over x minus c, this difference quotient is always bigger than or equal to 0. So we've established this for all points x and c in my interval. So if that's true for all points in that interval, then when I take the limit of both sides as x approaches c, it should still be true. And so in particular, why is that cool? Because this is just f prime of c. So we've established that f prime of c is at least 0 for every point c and I, which is exactly what we wanted to show. I just used the letter C instead of the letter X is all that we've done. So we've again established that rule that you probably remember from calculus, where if the derivative is positive, that means your function is increasing, and vice versa. If your function is increasing, it's got to have a positive derivative at those points. And then similarly for decreasing and negative derivatives. All right, so what we're going to do is we're going to use that to establish what was called the first derivative test. And so this is a test to try to locate the relative extrema of your function. So hills and valleys, how do you find them? So let's say you've got a function f that's continuous on this closed interval from a to b, and let's say that c is a point between a and b. Assume that f is differentiable between a and c, and also between c and b. So I don't care much if it's differentiable at c or not. Then the following should happen. So 1, if you can find a neighborhood, so around c, say c minus delta, c plus delta, that's still contained entirely in your interval that you're playing with, such that on that interval the derivative is non-negative, then, so the derivative is non-negative as long as x is, again, to the left of c, but in that little neighborhood, and the derivative is non-positive as long as x is to the right of c, but in that little neighborhood. Well, then what has to happen? F has to have a relative max at c. And so how do I visualize all this good stuff here? I'm hoping that I've got a picture that helps clear things up. So I'm trying to say, if I'm in this interval from c minus delta to c, if you pick an x value in there, and it happens to be the case that the derivative is non-negative, well then that means that the slope of the graph there is a non-negative number, so the tangent line looks something like the blue. Or, on the other hand, when we're to the right of c, we've got a non-positive derivative, so the slope of the tangent line maybe looks something like that, a yellow there. What do you see happens? Right, the derivative changes sign at c. And so the point then is that c would have to be a relative maximum. C has to be a hill. And number 2, it's a pretty similar statement to try to show a relative minimum. Maybe what do you notice? The derivative is non-positive when you are in your interval but to the left of c, and the derivative is non-negative when you are in this interval but you are to the right of c. Then f has a relative minimum. And so again here, I'm saying if you pick an x value in here and you get a non-positive derivative, but then it switches to this side, if you pick any x in here and it gives you a non-negative derivative, then what happens at c? Well, that's where the sign of the derivative changes from negative to positive. Therefore, that is where c has to have, your graph has to have a hill. No, it's not a hill, sorry, it's a valley, right? It sinks in, it's a minimum, it's a relative minimum. No more landscapes, it's a relative minimum at c. All right, so what we're going to do, just like above, these two things are pretty similar to each other. Let's just prove number 1 together. So let's say that I've got a point that is strictly between c minus delta and c. So in other words, it's in my little window that, again, if you read number 1, like if this happens, so I'm going to assume that there is such an interval here such that this good stuff happens. What do I need to show? Well, the thing I need to show, I probably shouldn't have picked red to do this, is that f has a relative minimum. So I get to assume all that good stuff that I've highlighted. So let x be between c minus delta and c. So what we'll do is, well, like usual, we'll apply the mean value theorem to this function f from this interval from x to c. And I'll switch back to yellow. So there exists some number, I'll call it c sub x just because it depends on whatever that x is, say, such that though, again, my kind of usual equation from the mean value theorem, f of c minus f of x is equal to f prime of this number cx times c minus x. So again, just to emphasize, this x is just notation, it's a subscript on c here. So by hypothesis though, what did I get to assume? I got to assume that f prime of cx is bigger than or equal to 0 because cx is in this interval from x to c, which is inside of this interval here. And if I think back up here, f prime is, am I looking at the right thing. Oh, f prime is non-negative whenever I am in that window. Cool. And so what else? So what does that mean? That means this is non-negative, and I know that this is positive since c is to the right of x. Therefore, this is bigger than or equal to 0. So why is that good? That tells me that f of c is bigger than f of x for every single x that's in my little neighborhood to the left of c. I highlighted the wrong thing, right? This is true for every x, again, in my little neighborhood to the left of c. And so now what we'll do is we'll jump to the next case. Well, what if x is on the other side of c in my little neighborhood? So again, now I'm going to try to prove this case here. Try to talk about what happens. And I'll try to show here, just like my picture suggests, I'll try to show again that f of c should be the tallest of any output for any input that's in this highlighted group of the domain. This highlighted c to c plus delta. And so again, we'll apply the mean value theorem. So now x is to the right of c, right, if it's in this interval here. So x is to the right of c, so I'll apply the mean value theorem to this interval from c to x. So again, I'll use the same notation. There exists some number c sub x such that, again, my same mean value equation. I'm not saying it's the same cx as above, it's just I'm going to use the same notation. So now what can we say? Well, in this case, this number cx is to the right of c, right? So in particular, it's in this interval here. And so what did I assume about that? If I go back up to number 1 here, I assumed that the derivative is non-positive whenever you took values that are between c and c plus delta. Great, so that justifies why I'm saying the derivative of cx should be non-positive. But then also what do I know? Well, I know that x now is to the right of c, therefore x minus c is a positive number, so that altogether this has to be a negative number, right? I've got a non-positive number times a positive number, so maybe I should say this is non-positive. And so this says non-positive, less than or equal to 0. And so what we'll do, we'll add that f of c over. So again, I get f of x is less than or equal to f of c. So notice that I was able to prove that no matter what side of c I'm on, right? I was able to prove that for each little interval from c minus delta to c and for c to c plus delta. And so the point then, what did we just establish? We just established that f of c is bigger than or equal to f of x for every single x in that neighborhood, which is the same thing as saying that f has a relative maximum at that point c. All right, let's do an application of the first derivative test. So let's say you've got this function, f of x is x cubed over 3 plus x squared minus 3x. So what I want to do is I want to find any relative extrema of this function. And so you're going to have some calculus 1 flashbacks, but just to emphasize, how do you use that first derivative test? And so if I look at the derivative, it should be x squared plus 2x minus 3. And what we'll do is we'll set that equal to 0. And so if I do that, I could factor that as well. So I tried to pick this function so that I think it factors nice. X plus 3 times x minus 1. And so I see that the derivative is actually equal to 0 if and only if x is negative 3 from here or x is equal to 1 from here. And now let me show you how I like to think about the first derivative test. I like to kind of make a diagram. So I've got a number line here, and I've plotted the 2 points that I found where I know the derivative is actually equal to 0. So now what I'm thinking about is, well, when I plot those points, that splits the number line into these 3 pieces here, these 3 little subintervals. What I'm going to do is I'm going to, kind of on the side, I've got f prime of x here. I'm going to pick a test point in each one of these subintervals. And you can pick whatever point you want, it doesn't matter. So I'll just pick ones out of convenience. -4 sounds cool, 0 sounded great, and 2 sounds fun. And what we'll do is we'll take this and we'll plug it in for x into, here's my derivative, and this is probably, in my opinion, the most convenient formula to plug it into. So I'm going to do that all at once for each one of these. But again, I'm just plugging the kind of tealish number in for x into this formula here. And all I really care about is what the sign is. And so in particular, like when you see this, this gives me a negative times a negative, which is a plus. And so it's positive. And so similarly here, positive times negative is negative when you plug in 0. And similarly here, positive times positive is positive. And so the point, what are we trying to say? We're trying to say the derivative f prime, well, this says it's positive for all numbers to the left of -3, right? If it was to change somewhere, that means you would have had to have a point where the derivative was 0, but that doesn't happen. And similarly, I'm saying that the derivative is negative for all points in this subinterval, and I'm saying the derivative is positive for all points in that subinterval. Now what we'll do is we'll use what we know about, well, what does the sign of the derivative tell me about the function f? Well, that tells me that derivative is positive, tells me the function's increasing on this interval, on this subinterval. Similarly, the derivative is negative on this subinterval, tells me that the derivative, or I'm sorry, my function f is decreasing. And I drew the arrows just to emphasize that, well, look, it changes from increasing to decreasing, therefore minus 3 should be a hill, right? It's a maximum, or a relative maximum, I should say. And then similarly here, at 1, you see that it changes from decreasing to increasing, so that means that's that 1 should be a relative minimum. And so, in my opinion, that's a nice way to keep track of using the first derivative test and to relate, again, the sign of the derivative to what the function's doing, and just seeing, do you change from increasing to decreasing or from decreasing to increasing, and then realizing that that tells you you've got a relative max in the first case or you've got a relative minimum in the second case.